In the early days, flying was a simple proposition. The pilot's technique was rather elementary. All he had to do was turn his cap backwards, slip on a pair of goggles, pull back on the stick, and hope for the best. Anything off the ground was considered good flying, unless you crashed into something. Any landing was a good landing, if you could walk away from it. But 40 years have brought the plane from a bundle of canvas, bamboo, and piano wire to a complex metal giant weighing tons, which remains in the air for hours at a time. And this change has brought new demands on the pilot. Flying is now a highly scientific procedure, and the accuracy required calls for every ounce of the pilot's skill and energy. To really appreciate this problem, let's watch a pilot in action. We will see how he controls his plane by means of his eyes, brain, nerves, and muscles. For example, suppose he has allowed the plane to fly nose down and wing low. The pilot, by means of his eyes, checks his reference points: the horizon, left wing, right wing, the compass, gyro flight indicator, rate of climb. The eyes see the error, and the nerves telegraph the message to the brain. The brain analyzes the information. Compass off, wing low, nose down, equals plane off course. The brain then decides what corrections to make: right rudder, right aileron, up elevator, and sends an order for these corrections to the muscles, which start to operate the controls. This only starts the correction. As the plane comes back on course, the nerves continue to send messages to the brain, which continues to analyze the situation. On course, stop. And at the proper moment, sends an order to stop the correction and return the controls to neutral. In the pilot, this simple correction produces fatigue, so slight that it goes unnoticed. But the accumulated effect of a number of these operations will slow down his reaction time. The time it takes a pilot to perceive an error and start a correction may be as fast as a quarter second. But as he becomes tired, his reaction time gets longer and longer until a danger point is reached. For instance, a pilot may be returning from a long flight. As he comes in for a landing, he appears to function perfectly. His eyes see the instruments. Throttles back, flaps down, red light. The eyes send the message to the brain, but the brain is tired and would rather think about a juicy steak, a refreshing drink, or other things. Even the warning horn fails to arouse him. Wheels up!
They said you had your head up. What does that mean?
With progress and development in aviation, it was inevitable that planes would become larger and more complex. In keeping step with this trend, equipment has been designed that relieves the pilot of constantly handling the controls on a long flight. This equipment is known as the C-1 Autopilot. When compared with the human pilot, the C-1 Autopilot can also be said to use eyes, brain, nerves, and muscles. The gyroscope takes the place of the human eye. The amplifier becomes the brain. The balancing circuits are the nerves, and the servo motors do the work of the muscles. These units function in a manner similar to the human pilot. The gyros see an error in flight, send a signal to the amplifier, which sends a current to the servo motors, which operate the control surfaces. To demonstrate this, let's put the various units of the autopilot into a plane and study their operation. First, the eye of the autopilot, the vertical flight gyro. By removing a section of the case, we see it contains a gyroscope so constructed that when spinning, it is held vertical to the earth. In its simplest form, the gyro is composed of two main parts: the gyro wheel and the bales which hold it vertical. The action of this gyro controls both the pitch and roll axis of the plane. Let's take up the pitch axis first. Here's a simplified cross-section of the vertical flight gyro. When the plane pitches, the gyro case moves with it, but the gyro itself remains vertical. This enables us to use the axis of the gyro as a fixed reference point. The angle of deviation thus formed can be measured electrically by means of the potentiometer. The potentiometer, or pot, which measures the angle of pitch, is called the elevator pot. Basically, it is composed of two parts: a wiper and a resistor. The wiper is attached to the gyro. The resistor is fixed to the gyro case, which in turn is fastened to the plane. When the plane pitches, the wiper, remaining vertical, measures both the amount and the direction of the pitch. Now let's see how the gyro pot signals this information to the elevator. Here is the pot in diagram form. By placing the pot in a parallel circuit, we form a bridge circuit. Now we apply a source of power to operate the circuit. As long as the wiper remains centered, the circuit is in balance, and no signal will be sent. But if the wiper is moved off-center, the circuit is thrown out of balance, and a voltage signal is created. When the wiper is returned to center, the circuit is once more in balance, and the signal stops. When the wiper is moved to the left of center, the signal goes through in one direction. When the wiper is moved to the right of center, the signal goes through in the opposite direction. In actual practice, of course, the wiper remains stationary and the resistor moves. In order to make the signal strong enough to be effective, an amplifier is added to the circuit. The amplifier is similar to that used in an ordinary radio. When a signal is received from the pot, the amplifier boosts it up and sends it to the servo unit. The servo unit is composed of two main parts: the motor, which rotates continuously in one direction, and the cable drum, which is geared to operate in either direction. Now, when the pot is moved off-center to the left, the servo rotates clockwise. When the pot is moved off-center to the right, the servo rotates counterclockwise. In actual operation, the units act simultaneously, but for demonstration purposes, we will move them one at a time. In level flight, the gyro pot is centered, but as the plane tilts, it throws the gyro pot off-center, sending a signal through the amplifier to the servo. The servo applies up elevator, which returns the plane to level flight. The gyro pot moves back to center, and the signal stops. But the elevator cannot be left in up position. Therefore, the servo must be reversed in order to return the elevator to neutral as the plane resumes level flight. This is accomplished by a second pot, which is placed on the servo cable drum. Now, let's see how this works into the bridge circuit. This represents the pot on the servo. And this, you remember, represents the pot on the gyro. Now we complete the circuit. When the plane tilts, the gyro pot is moved off-center, unbalancing the circuit, thereby sending a signal to the servo. The servo cable drum turning causes the servo wiper to move along the resistor to a point where it balances the circuit. This stops the signal and consequently the servo rotation. As the plane begins leveling off, the gyro pot starts moving back towards center, which unbalances the circuit in the opposite direction, reversing the signal. This reverses the servo, which moves the servo pot back to center, balancing the circuit, and the signal stops. Now, remember the relationship between the two potentiometers. The gyro pot is controlled by the gyro. The servo pot is controlled by the servo. The circuit will remain in balance as long as the plane maintains level flight. Any deviation of the plane throws the circuit out of balance, simultaneously operating the elevator. Here we see the elevator bringing the plane back to level flight. Meanwhile, the gyro is returning the gyro pot toward center. This unbalances the circuit in the opposite direction, reversing the servo and gradually returning the elevator to normal as the plane resumes level flight. The pots are once more at center and the signal has stopped. This is the fundamental principle of the C-1 Autopilot. A plane in level flight has a certain physical balance, but when flying the C-1 Autopilot, it has an electrical balance as well. When the ship loses its physical balance, the electrical balance, being the stronger of the two, brings the ship back to its correct attitude. You have seen how the vertical flight gyro controls the pitch axis of a plane. This same gyro also controls the roll axis. This is done through a second pot on the gyro called the aileron pot. The aileron pot functions like the elevator pot. As the ship rolls, a signal is sent through the amplifier to the aileron servo unit. The servo operates the ailerons and corrects the error. In this axis also, the plane has both a physical and an electrical balance. If the plane rolls, the electrical balance will correct the error. Remember, too, that the electrical balance in both the pitch and the roll axis is controlled by the vertical flight gyro. The yaw axis of the plane is controlled by another gyro called the directional stabilizer. As seen from above, when the plane yaws, the axis of the gyro remains fixed in one direction. Again, the wiper of a pot is fastened to the gyro and the resistor fastened to the gyro case. Let us say that the plane is headed due north. If the ship is thrown off its course, it will force the pot off center. The circuit, being unbalanced, sends a signal to the servo, which operates the rudder. The rudder corrects the heading, and both pots return to center. Here again, we have both a physical and an electrical balance. When the plane yaws, the electrical balance brings the plane back on its course. The question arises, what if the pilot wants to change his course? Some way must be found to prevent the stabilizer from sending a signal. This is accomplished by adding a locking device to the stabilizer. When a change in course is desired, the lock is engaged. As the plane turns, the wiper turns with it, and no signal is sent to the servo motor. When the turn is completed, the lock is disengaged. The directional stabilizer will now keep the plane on its new course. Or in other words, when a turn is desired, the electrical balance of a plane can be shifted with the plane. Thus we see that the C-1 equipment controls the plane in much the same manner as the human pilot. But there is this important difference. In the autopilot, the reaction is practically instantaneous. The moment the gyros detect an error, the correction is being set in. The autopilot, relieving the human pilot of many of his routine duties, takes the drudgery out of long flights. But it has a still more important purpose. It provides the bombardier with a stable platform and holds the plane on course during the bombing run, a function which we will cover more fully in subsequent pictures of this series. Piano wire to a complex metal giant weighing tons, which remains in the air for hours at a time. And this change has brought new demands on the pilot. Flying is now a highly scientific procedure, and the accuracy required calls for every ounce of the pilot's skill and energy. To really appreciate this problem, let's watch a pilot in action. We will see how he controls his plane by means of his eyes, brain, nerves, and muscles. For example, suppose he has allowed the plane to fly nose down and wing low. The pilot, by means of his eyes, checks his reference points: the horizon, left wing, right wing, the compass, gyro flight indicator, rate of climb. The eyes see the error, and the nerves telegraph the message to the brain. The brain analyzes the information. Compass off, wing low, nose down, equals plane off course. The brain then decides what corrections to make: right rudder, right aileron, up elevator, and sends an order for these corrections to the muscles, which start to operate the controls. This only starts the correction. As the plane comes back on course, the nerves continue to send messages to the brain, which continues to analyze the situation. On course, stop, and at the proper moment sends an order to stop the correction and return the controls to neutral. In the pilot, this simple correction produces fatigue, so slight that it goes unnoticed, but the accumulated effect of a number of these operations will slow down his reaction. In the early days, flying was a simple proposition. The pilot's technique was rather elementary. All he had to do was turn his cap backwards, slip on a pair of goggles, pull back on the stick, and hope for the best. Anything off the ground was considered good flying, unless you crashed into something. Any landing was a good landing, if you could walk away from it. But 40 years have brought the plane from a bundle of canvas, bamboo, and